Welcome to the demonstration series of Physics 141. Today, we'll be looking at the pendulum. A pendulum is a mass swinging back and forth on a string. And today we are going to investigate how does the length of the string influences the period of oscillation. And a period is the time it takes for the mass to have a complete cycle, meaning a back and forth motion. We are also going to investigate how does the mass of the pendulum bob could affect that period of oscillation, and also the amplitude of oscillation, which is the maximum angular displacement from the equilibrium position, which is at the lowest point of the swing. So let's start the experiment and let's do it backwards. Let's start first with the dependence on the amplitude. So I'm going to take an amplitude of about 10 degrees, and I'm going to measure 10 periods of oscillation, because by measuring 10 periods, we are going to get a more precise measurement than doing 10 times one by one measurements. So let's start then again. We have, as I said, an angle of 10 degrees. 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 took 1363 seconds. So 10 took 1363 seconds. This means that the period tau for the case of 10 degrees is 1.36. Now we are going to repeat the measurement, but at 5 degrees. So the amplitude now will be 5 degrees. Repeating the same process, starting again at 5 degrees. Now we have 5 degrees. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, 1363 seconds. So exactly the same amount. So for a 5 degree amplitude, tau again is 1.36 seconds. This is the total time, and it was 13.63, and this was the angular aperture, that was 10 degrees, and for 5 degrees we got exactly the same result. This means that there is no influence in the amplitude on the oscillation period. So now that we know there is no influence in the amplitude on the oscillation period, let's see what happens when instead of taking a key, we take a washer. So we move it again about 5 degrees, and we are going to take 10 swings again. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we got 13.47 seconds, which means, again, that the period is 1.36 1.37 seconds, 1.36, 1.37. There is absolutely no difference in the period when we change from the washer to the key. And let's convince ourselves that the period of oscillation is completely independent of the mass. And for that, we are going to do the same thing with the nut. We move something like 5 degrees. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We got 13.78 seconds. So this means that, again, there is absolutely no difference in the period of oscillation. In all the cases, it's something like 1.37. Let's round to 1.4. Okay? So the period of oscillation for a string of 50 centimeters with a key, with a washer, and with a nut is 1.4 seconds. Now, let's see what happened when we take a shorter length of the string. So we are moving 5 degrees, and we are going to repeat the process. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here we got 10.84 seconds. So clearly there is a difference here. And so when the length is 30 centimeters, we get a period of 1 second, because 10 divided by 10 is equal to 1. So this one is 1 second, this is 1.4 seconds. So let's see what happened in the last case when we have a string of 70 centimeters. So again, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So in this case, we got 16 seconds, which means that the period is 1.6 seconds. So, to summarize, first we show that the period is independent of the angular amplitude. Then we show that it's also independent of the mass of the pendulum bob. And then we got the relation that there is a dependence with respect to the length of the string. And this one is for 30 centimeters. This one is for 50 centimeters. And this one is for 70 centimeters. Actually, in class, we have seen that the period of a pendulum depends on the length and on gravity, on the acceleration of gravity near the Earth's surface. So actually, we have seen that the period of a pendulum is 2 pi times the square root of the length divided by g. Again, g is the acceleration of gravity, 9.8 meters per second squared. And so we have 3 different lengths here, 0.3 meters, 0.5 meters, and 0.7 meters. So you can convince yourselves, substituting 0.3 divided by 9.8, you take the square root, you multiply by 2 pi, and you are going to get 1 second. If you do the same with 0.5 divided by 9.8, take the square root, you multiply by 2 pi, and you are going to get 1.4 seconds. And when we do this for 0.7 meters, we get something like 1.7 seconds. So we can see that our experiment really matched the prediction of the formula discussed in class. And this is all, folks.